Manual transmissions are often described as simple, durable, and entirely under the driver's control. And that's exactly where a potential risk to their longevity begins. Because most of the wear inside a manual gearbox doesn't come from obvious mistakes. It comes from small, repeated habits that feel completely normal while driving. So if you've ever wondered why some manual transmissions stay smooth for hundreds of thousands of kilometers, while others start grinding much earlier, this video is for you. The 5 habits we'll cover rarely cause immediate failure. Instead, they create microscopic wear in synchronizers, bearings, clutch surfaces, and gear teeth. Over time, that wear adds up, eventually showing up as rough shifts, slipping, or vibration. To understand why, we need to look briefly at what's happening inside the transmission when you drive. A manual gearbox is a system of rotating shafts, meshing gears, and synchronizers that match speeds before a gear engages. The clutch temporarily disconnects the engine so you can shift. And the synchronizers use friction to bring components to the same speed. Every shift is essentially a controlled friction event. Wear increases when the energy that has to be absorbed during that process becomes higher than intended, often because of how the driver interacts with the system. The first and very common habit is resting your hand on the gear lever while driving. It feels natural, but the gear lever is mechanically linked to selector forks inside the transmission. Even a small, constant force can press those forks slightly against rotating components. That creates continuous, low-level contact where there should normally be none. Over time, this adds friction to synchronizer parts and can slowly affect alignment. The change is gradual, but it often shows up later as notchy or less precise shifting. What makes this more significant is repetition. Synchronizers are designed for brief, intermittent contact during shifts, not continuous loading. In practice, even a relatively small input force at the gear lever, on the order of 5 to 10 newtons, gets transmitted through a largely undamped mechanical linkage into the transmission. Over thousands of kilometers, that translates into millions of micro-contact events between the synchronizer friction surfaces. Each individual event removes a negligible amount of material, effectively invisible in isolation, but the cumulative effect is not. This gradual material loss changes internal clearances and shifts the geometry the system relies on. Once those tolerances drift beyond design limits, the synchronizer has to work harder to do the same job. More force is required, more time is needed to equalize rotational speeds, and the probability of gear clash or grinding increases, especially during fast shifts. The second habit is holding the car on an incline using the clutch instead of the brake. In that situation, the clutch is not fully engaged or fully disengaged. It is slipping continuously to balance the car against gravity. That slipping converts mechanical energy into heat inside the clutch disc. For a typical car on a moderate incline, the clutch has to hold a significant force just to keep the car stationary. Maintaining that through slip generates a steady thermal load. Unlike a normal start where the clutch slips briefly, this heat builds up in one area and can create hot spots. Over time, the friction material degrades, and the clutch starts to lose its ability to transmit torque cleanly. The result is earlier clutch wear and eventually slipping under load. The third habit is not fully depressing the clutch pedal during shifts. When the clutch isn't completely disengaged, a small amount of torque still passes through the drivetrain. That means the synchronizers now have to do more work. Instead of just matching speeds, they also have to overcome that remaining torque. This extra load increases the friction work required during each shift. It's especially noticeable during downshifts, where speed differences are larger. Over time, this accelerates wear on synchronizer surfaces and can lead to the familiar grinding noise when gears don't engage smoothly. The fourth habit is downshifting aggressively without matching engine speed, often called rev matching. When engine speed is too low for the lower gear, the synchronizer has to spin up the internal components to the correct speed before engagement. That energy comes entirely from friction. What matters here is that the energy required increases quickly with speed difference. A larger mismatch doesn't just create slightly more wear, it can create several times more. Repeating this over time can glaze the synchronizer surfaces, making them less effective. The transmission may then start to resist quick shifts or require slower, more deliberate inputs. The fifth habit is resting your foot on the clutch pedal while driving, sometimes called riding the clutch. Even slight pressure can partially disengage the clutch, reducing the clamping force between the clutch disc and flywheel. That leads to small but continuous slip, even when you're just cruising. This type of wear is easy to miss because nothing feels obviously wrong. But over long distances, it steadily reduces clutch life and can create uneven wear across the friction surface. Like the other habits, the damage comes from duration, not intensity. Across all of these examples, the pattern is the same. Manual transmissions rely on precise control of friction and energy. When driver inputs increase the amount of energy that has to be dissipated, whether through extra load, larger speed differences, or longer contact time, internal components wear faster. This isn't unique to cars. The same principles apply in industrial gearboxes and other mechanical systems. They are designed for controlled, short-duration friction events, not continuous or excessive energy input. When those limits are exceeded repeatedly, wear accelerates. A relevant historical case can be found in early commercial vehicle fleets during the mid-20th century. Drivers often used clutch slip to control speed on inclines and during low-speed maneuvers. Fleet operators observed significantly reduced clutch life, sometimes by more than 50% compared to expected service intervals. Engineering analysis revealed that thermal degradation of friction materials was the primary failure mode. This led to changes in driver training and the adoption of more robust clutch materials, but the underlying physics remained unchanged. It's also important to understand that transmissions are designed with safety margins. Occasional mistakes won't destroy the system, but consistent exposure to higher loads gradually uses up those margins. Temperature, lubrication, and material properties all interact. For example, higher temperatures can reduce oil effectiveness, increasing internal friction and compounding wear. At a system level, manual transmission wear is essentially an energy management problem. Every shift and every clutch interaction involves converting motion into heat through friction. Habits that increase that energy, even slightly, add up over time. The system doesn't fail immediately, but the long-term effect becomes visible. The practical takeaway is straightforward. You don't need perfect driving technique, but small adjustments make a measurable difference. Keeping your hand off the gear lever, using the brake on inclines, fully disengaging the clutch, and matching engine speed during downshifts all reduce unnecessary stress on the system. In the end, the lifespan of a manual transmission is not just determined by its design, but by how it is used. Most of the damage is not caused by one big mistake, but by many small ones repeated over time. Understanding the underlying mechanics, friction, heat, and energy makes it much easier to avoid those patterns and keep the transmission operating as intended. If you found this breakdown useful and want more system-level explanations, consider subscribing to Engineering Manual.